Is the screen visible?
Yes, ma'am.
Okay. So in the last class, we have started discussing. We started with analysis of transfer lines. In analysis of transfer line, we have these two subtopics that we had to look into. So we have already seen what is this transfer line with no internal part storage, and we in that we have seen some assumptions that need to be done, and after that we have seen how we can find the cycle time, that is tc is equals to max of ts, that is setup time, plus the transfer time tr. Then we found out what is tp, how to find tp. Tp is given by tc plus f into td. And then we have two approaches, upper bound and lower bound approach. And in both of these approaches, we can separately find the value of f and rp. So we have already discussed those things, and we have noted down the equations as well for upper bound and lower bound approach. And then it comes to finding out the line efficiency. It is given by TC by TP. And so line efficiency, or you can even call it as the proportion of uptime. And then we have also seen the proportion of downtime, that is D, which is given by F into TD upon TP. And then finally, we have determined the cost per piece. How to determine the cost per piece? We have seen that it is given by CM plus C naught TP plus CP. That is material cost plus the actual operation cost plus the cost of the tool or the tooling cost. So these were few equations that we have already come across, and that all of this is with respect to transfer line with no internal part storage. Today we will be discussing the last part of this unit number 2, that is transfer line with internal storage buffer. And today we will be finishing with unit 2. There was a request from your end that the Thursdays and Fridays classes should be taken on Monday. So as I already mentioned, until my first year classes start, I will do the needful. I will take your Thursday, Fridays class on Monday. As you know, in this week again on Friday we'll be losing the class because I think it's a holiday on Friday. So only for this week I'll take 1 hour class on Thursday. From next week we will take the class on Monday, Tuesday, and will not take it on Thursday, Friday until the first year classes start. So only for this week, that is on the coming Thursday, we will have just one hour class, that is 45 minutes effectively, and we will start with unit number 3. Okay. I hope this is clear.
Yes, ma'am.
Okay. So to start with the transfer line with internal storage buffer, I have actually started discussing this point, this topic in the last class itself, but I'll just quickly go through it once again. When it comes to these transfer line with internal storage buffer, there are these two concepts of starving and blocking that are very important for us to understand. And we have already spoken about starving and blocking when we were studying about the storage buffer. Okay, why buffer storages are important. Okay, so one of the concept is starving. So what is starving? Starving on an automated production line, it means that a workstation is prevented from performing its cycle because it has no parts to work on. Okay, and that means what? Whenever there is a breakdown in any of the workstation, it will all the work parts will get blocked there itself. They will not be moving to the downstream station. That is, they are not moving to the next station. So the downstream station, which is waiting for the parts to be bought in for to carry out the operation, it will be starving. It will not have any work parts to work on. Okay, so when a breakdown occurs at any workstation on the line, the downstream station will either immediately or eventually become starved for parts. And what do we mean by blocking? Blocking means that a station is prevented from performing its work cycle because it cannot pass the parts just completed to the neighboring downstation. So the station, uh, which is there, if suppose if it is stopped for some reason, the station before it will get blocked with all the work parts because those work parts cannot be transferred to the immediate next station. Okay, so starving and blocking basically have the same meaning as we all know, but it is just applied here in these automated production lines. So whenever a breakdown occurs at a station on the line, the upstream station becomes blocked because the breakdown station cannot accept the next part for processing from its upstream neighbor. Therefore, none of the upstream stations can pass its completed parts forward. So downtime on an automated line due to starving and blocking can be reduced by adding one or more part storage buffers between stations. So as I said, downtime is the time for which the workstation or your automated production line will not be functioning. The time for which it is not actually carrying any of its task. Okay, so that time is something that we always want to try and reduce because time is a very important factor whenever it comes to production. We try to finish the things as soon as possible in the given time frame. So here one of the major concerns when it comes to manufacturing industries is time. So if you can cut short or cut down on the downtime, then it is going to be helping you to increase the efficiency of the manufacturing sector or that particular industry. So we are always going to try and reduce the downtime, and this can be done by accommodating the storage buffers in between the workstations. Okay, so as I said, storage buffers you can have maximum n minus one storage buffers in line. Suppose if you have 10 stations, you can have maximum 9 buffer stations in line. You can place them uh, just in between two stations, or you can divide the complete station into stages and then you can place the buffer storages. So storage buffer, it basically divides the line into stages that can operate independently for a number of cycles. The number depending on the storage capacity of the buffer. If one stage, sorry, if one storage buffer is used, the line is divided into two stages. If two buffers are used, then it will be divided into three stages and so on. Therefore, for n stage lines, there will be n minus one storage buffers. So I'm just running through these slides because these points are already discussed in the previous class. Just in order to have that connectivity, I have just started again with the topic. So now let us consider this case of two-stage transfer line with the storage buffer separating the stage. So just imagine, suppose if you have 10 workstations in a line, you're going to divide it into 5 stations at one side and 5 on the other side, having one storage buffer located in between them. So stage 1 has first 5 workstations, then you have a storage buffer, and then you have the next 5 stations. So one storage buffer used here, which is dividing the line into two stages. So now let us suppose that on average the storage buffer is half full. Now I request you all to please pay attention to all the points that we are discussing and to come across because these are very important. And if you're not very much attentive or if you're not noting them down correctly, you are likely to get confused here. Okay. So just I'm giving you maybe an extra minute to just write down the important points henceforth after this. Okay, so now let us suppose that on an average, the storage buffer is half full. So as I said, storage buffer, it will have its own capacity. Okay, so here it is mentioned in the line above it. Okay, there is something called as capacity of the storage buffer, and we denote the capacity of the storage buffer by alphabet B, small b. Okay, by capacity, what do we mean? Suppose if B is equals to 10, that means the storage buffer is capable of accommodating 10 parts. If I say that the buffer storage capacity, that is small b, is 100, that means that location, the storage buffer is capable of holding 100 parts. Okay. So if the first stage breaks down, now we are considering this case of two-stage transfer line with one storage buffer in between, and we are assuming that on an average that storage buffer, it is half full. Okay, we haven't discussed in any quantity as to what is the capacity of the storage buffer. We are just saying that whatever may be the quantity, okay, whatever may be the capacity of the storage buffer B, it is half full. So, if the first stage breaks down, that is 1 to 5 workstation, in case there is some reason for it to break down, then what happens? The second stage can continue to operate. It will not face any starving. It will not be waiting for any work parts to be bought in. Even though the stage 1 has broken down and has stopped functioning, the stage 2 will still continue to function. So if the first stage breaks down, the second stage can continue to operate using the parts that have been uh, stored or which have been collected in the buffer storage. So what happens? All the parts that have been operated or operations have been carried out on them. They move from station 1, 2, 3, 4, 5, and then they go and settle down into the location that is storage buffer. Okay. So suppose if workstation 4 breaks down for some reason, then the complete stage is going to be halted for some time. Okay. So what happens? The 6, 7, 8, 9, 10 workstations which are there, they are not going to get affected by this because there are parts which are already stored into the buffer storage, and those parts will be one by one supplied to station number 6, 7, 8, 9, 10, and they will continue to function. Okay, if the storage buffer was not there, then because suppose if the station 4 has stopped, 5, 6, 7, 8 would not receive any parts to work on. So this is what happens, and until that capacity of the storage buffer is there, until it gets exhausted, the second stage can still go on functioning. Okay, and meanwhile the first stage will get repaired or whatever was the reason for breakdown, and again it will resume its work. And if the second stage breaks down, the first stage can continue to operate without blocking. It will avoid blocking because of the buffer. The buffer, it is going to go on receiving the outputs. So suppose if station number 6 has some problem, the parts that are produced in the station number 1, 2, 3, 4, and 5, they will continue its functioning. That stage will not get affected because whatever are the parts that are made in the first stage, they get collected into the buffer storage. So there is a path for the parts that are made to go out instead of getting blocked there itself. Okay. So next is limits of storage buffer effectiveness. There are these two extreme cases of storage buffer. Now, it's very important to understand how basically the capacity of these storage buffers. So, there are these two extreme cases of storage buffer effectiveness, and they can be identified as first one, that is no buffer capacity at all. Okay, so just imagine again the same automated production line of 10 workstations with one storage buffer which is placed in between the two stages, that is divide the 10 stations into 5 plus 5. Okay, so you imagine that storage buffer to have zero capacity. So the first the basically the first case that we see here is no buffer capacity at all. Though we say that we have a buffer storage, but it has zero capacity. It's as good as not having any storage buffer. And the second extreme case here is infinite capacity storage buffer. So you can just think of these two cases. You have a storage buffer which has zero capacity, which is as good as having no storage buffer only. And there is another case which has infinite storage capacity. You can dump as many number of work parts you want in that particular workstation. It will be having this infinite capacity. So these are the two extreme cases considered here. In the analysis that follows, let us assume that the ideal cycle time is the same for all stages considered. So here also we have these assumptions made. So the first assumption that we make here is that we consider that the cycle time is the same for all stages considered. So if you have one stage, two stage, three stage, whatever number of stages, all will have the same cycle time. In case of no storage capacity, the production line acts as one stage. Yes, it's very much obvious. If you are going to imagine this 10 station automated production line, and I say that there is one buffer storage in between, and if I say that the storage capacity is zero, it's as good as not having any storage buffer. So that becomes a case of production line which is of one stage, right? Because it is not going to, that storage buffer is of no use here because it cannot hold any parts in it because it has zero capacity. So when a station breaks down, the entire line is going to stop in that case. This is the case of production line with no internal storage analyzed. Okay, so if you consider this first case here, no buffer storage at all, it is nothing but similar to the analysis that we have already studied in the previous class, that is analysis of production line with no internal storage. So we rewrite the line efficiency here as the line efficiency of zero capacity storage buffer. So please write down this equation E naught. If you can check the equations for analysis of analysis of transfer line with storage buffer, you get the same equation there and here as well. Then the line efficiency is given by Tc upon Tc plus F into Td. So we have the same thing here also, because this first case of zero capacity storage buffer is considered to be similar to analysis of transfer line with no part storage or no internal storage buffer. So it's obvious when we consider it that the storage buffer storage has zero capacity. We are just writing this subscript 0, that is E naught. It is given by the same equation, Tc upon Tc plus F into Td. You need to write down efficiency of zero capacity storage buffer. E naught is Tc upon Tc plus F into Td. So where the subscript 0 identifies E naught as the efficiency of line with zero storage buffer capacity. So the opposite extreme is a theoretical case where buffer storage, the buffer zone of infinite capacity are installed between every pair of stages. So please just imagine that we are talking about automated production lines in which we are talking about the buffer storage is having zero capacity as one case, and the second case is a buffer storage having infinite capacity. But practically, if you see, both of these conditions are they are not the reality. Okay, the reality is going to be something in between these two extreme conditions. So if you have a storage buffer, it is surely going to have some capacity. That is, either it will have the capacity to hold 10 parts, 100 parts, 1000 parts, and so on. But it will have certain capacity, and that capacity will be specified. Whereas we are discussing these two cases, these are the extreme cases. One is having zero capacity and one is having infinite capacity. But in actual practice, you will see that the buffer storage capacity will be in between these two extreme cases. Okay, so now let us see for the opposite extreme case, that is having buffer storage having infinite capacity, what are the equations? So if we assume that each buffer zone is half full, then each stage is independent of the rest. Obviously, because we are imagining the buffer storage to have infinite capacity, that means both the stages are going to work independent of each other, because they are going to have the work part supplied at any point of time, because the capacity is infinite. Practically this is not possible, but in order to arrive to some conclusions as and when we proceed, these are the two extreme conditions taken into account. So the presence of infinite storage buffer means that no stage, okay, uh, no stage will ever be blocked or stopped because of the breakdown at some other stage. But of course, an infinite capacity storage buffer, it cannot be realized in actual practice. Okay, it is practically not possible. I hope you all are following. Have you all written down this equation, equation number 11?
Yes, ma'am.
So for all transfer lines with storage buffer, the overall line efficiency is limited by the bottleneck stage. Yes. As a practical matter, therefore, the upper limit on the efficiency of entire line is determined by the efficiency of the bottleneck stage. Given that the cycle time Tc is the same for all stages, yes, this is the assumption that we have made when we started discussing this point, this particular topic. We have assumed that the cycle time is the same for all stages. The efficiency of any stage k is given by. Please note down this equation. Where subscript k is used to identify the stage. So the overall line efficiency would be given by. So now we are talking about the line efficiency when the buffer capacity, the buffer storage capacity is infinite, right? So when we talk about this infinite storage capacity, we have taken into consideration the efficiency of stage K, and this basically is dependent on the bottleneck stations. Okay, so we have this the overall line efficiency. It is given by E infinity is equals to minimum of Ek for k is equals to 1, 2, and so on up to k. Please note down this equation 12 and 13. Okay, shall we proceed? Shall we proceed?
Yes, ma'am.
Okay, so as I said, the actual value of line efficiency for a given buffer capacity B will usually fall somewhere in between the two extremes. That is, now we have found an equation for E naught, it is Tc upon Tc plus F into Td. We know an equation for E infinity, it is minimum of Ek, we know the equation for Ek. But the actual, practically, you will see that there is some buffer capacity, and with respect to that buffer capacity, you will then have to find what is the actual line efficiency. Okay, so this is our concern, and we basically are trying to tell you what here is that when it comes to the two extreme cases taken into consideration of zero capacity and extreme or the infinite capacity, practically there is something that lies in between these two extremes. Okay, so here, now let us consider the problem of evaluating EB for realistic levels of buffer capacity uh, for a two-stage automated production line. That means what? You have two stages, that is k is equals to 2. If it was three-stage, k is equals to 3 and so on. So now let us analyze the two-stage transfer line. Okay, so here we are only going to see these two stages, that is analysis of two-stage transfer line. And after we understand this, we will just brief you about what is this analysis of more than two stages. Okay, there is no difference in these two things. That becomes a multi-stage line. This is just these two-stage transfer line analysis is what we'll first look into. So the two-stage line is divided by a storage buffer of capacity B expressed in terms of number of parts it can store. So as I said, the capacity of storage buffer, it is determined, or it is given by this, not given by, it is uh, yeah, it is determined by this alphabet small b. So the buffer receives the output of stage 1 and forwards it to stage 2, temporarily storing any parts which are not immediately which are not needed by the stage 2. So here the buffer, it basically receives the output of stage 1 and forwards it to stage 2, temporarily storing any parts not immediately needed by stage 2 up to its capacity B. So until it has its capacity B, there is no problem with respect to starving and blocking. It can help the production line go smoothly irrespective of the breakdowns at any of these stages. The ideal cycle time TC is the same for both stages. This is an assumption that we have made already. We assume the downtime distribution of each stage to be the same with mean downtime, that is TD. This is also yet another assumption made. So let F1 and FP be the breakdown rates of stage 1 and 2 respectively, and they are not necessarily equal. So what is F1? What is F? Basically, we have already known what is this F. It is the frequency of breakdown, F. Okay, and if, when we consider the upper bound and the lower bound approach with respect to analysis of transfer line with no internal part storage, we came across the equations to find out F. Okay, so here they are saying that let F1 and F2 be the breakdowns associated with each stage, because we are taking two stages here. So F1 is the frequency of breakdown at stage 1 and F2 is the frequency of breakdown at stage 2. They need not be equal. Okay, F1 and F2, they necessarily may not be equal. The overall line efficiency for the two-stage line, it can be expressed as, this is very important equation. Please note down this equation. So the efficiency of the line with buffer capacity of B is given by this equation. E naught plus B1 dash H of B into E2. Where EB is overall line efficiency for a two-stage line with buffer capacity B. E naught, it is line efficiency for the same line with no internal storage. The second term on the right hand side, that is D1 dash H of B E2, represents the improvement in the efficiency that results from having a storage buffer with B greater than 0. So please note down this equation, it's very important equation.
Done, ma'am.
Yes.
Done, ma'am.
Yes. What happened?
Over, ma'am. Continue. You can continue.
Huh?
Over, ma'am. It's written down the equation.
Okay. So when you see this equation number 15 here, right? We know how to find E naught. That equation we have already noted down. We also know how to find E2. E2 here is nothing but Ek, where K represents the number of stages. So we have two stage taken into consideration. Therefore, E2, which is nothing but the Ek equation, that also we know. But we do not know how to get the solution for d1 dash h of b. So let us now proceed with that. So let us now examine the right hand side term in equation 15. The value of E naught is given by equation 11, but we write it next to explicitly define the two-stage efficiency. So when B is equals to 0, you write E naught is equals to Tc upon Tc plus F1 plus F2 into Td. Why? Because we are talking about two stages and F1 and F2 may not be equal to each other. So when we find the line efficiency, considering that the buffer capacity is 0, this is the equation. So please note down this equation. When B is equals to 0, E naught is given by this equation.
Ma'am, F1 and F2 are the number of breakdowns, right?
Frequency of breakdown, yes. Here with respect to each stage. For first stage it is F1, for second stage it will be F2. So the term D1 dash, it can be thought of as a proportion of total time that stage 1 is down, and it is defined as follows. So D1 dash is given by F1 into TD1 upon TC plus F1 plus F2 into TD. This is equation number 17. I hope you all have written down these two equations 16, 17.
Yes, ma'am.
So now, as I said, if you consider this equation number 15, now we have also seen an equation to find D1 dash. We know how to get E naught, E2, but we do not know how to get H of B. So here, the term H of B is the proportion of downtime, that is D1 dash, that stage 2 could be up and operating within the limits of storage buffer capacity B. So finally, E2 corrects for the unrealistic assumptions in the calculations of H of B that both stages can never be down at the same time. So there are these possibilities, right? That now we are just assuming that maybe one stage is broken down, the other stage is functioning fine. But what if both the stages are going to break down at the same time? So this term E2, it basically corrects the unrealistic assumptions that the stages will never be down at the same time. So this E2 basically is like the or EK value that you can say. It is nothing but an corrective factor which is taken into consideration there. So this E2 is calculated as follows. E2 is Tc upon Tc plus F2 into Td. This is with respect to two stages. Okay, so we are not only interested in the line efficiency of two-stage production, we also want to know the corresponding production rate. So line efficiency, okay, we have already seen how to get the line efficiency for a two-stage production line having a buffer capacity V. So we also want to know what is the production rate because that is one of the measure of performance. So here we know that E is equals to Tc by Tp. Please note down this equation. We already have come across this equation, line efficiency, it is given by Tc by Tp. And we also know that the rate of production Rp is 1 by Tp. So combining these two equations, we get E is equals to Tc into Rp. So rearranging all these terms, you get rate of production Rp as E by Tc. So this is your equation number 19. So please note down. So when it comes to analysis of transfer line with the internal part storage, and when you are solving a problem having two stages, that time the rate of production is given by E into E upon Tc. So Rp will be, so we are just rearranging this. Rp will be E by Tc. Okay. Now here we have found out the equation for line efficiency, and we have also found out the equation to find out the rate of production RP. Okay. But as it is, you can see the equations for E naught, E2, D1 dash. We haven't still found out the equation for H of B. This is also very important here. Okay. So basically, we have these two persons. One is Buzakot. He's one of the experts in this area who has come up with some equations in order to find this h of b by using the Markov chain analysis. Okay, so we are not getting into the analysis part in order to find out these equations. We are just going to look into what are those equations, and we will use those equations to get the value for h of b. Okay. So now these equations are again very important. Okay, I will discuss these equations after a 10 minutes break. But before that, I'll just tell you all about analysis of transfer line having more than two stages. Okay. So if the line efficiency of an automated production line, it can be increased by dividing it into two stages with a storage buffer between, then one might infer that further the improvements in performance can be achieved by adding additional storage buffer. So when it comes to analysis of transfer line having more than two stages, basically you conclude or you will only observe that as you increase the number of storage buffers, okay, as the number of stages go on increasing, or the number of storage buffers included in automated production line are more, the better will be the efficiency of that automated production line, because of the breakdowns, the unexpected breakdowns that would actually lead to decrease in the efficiency, it can be avoided by using these buffer storages. Therefore, the solution or how to get the problem solved with respect to production lines having more than two stages are going to be on the similar lines. And for your syllabus, we are not getting into the problems with respect to multiple stages automated line. Okay, we will be stopping either at no buffer storage or two stages, only these two cases, and problems only based on this. But only one inference out of all of these things is that whenever you have more number of stages or you can say whenever you have more number of buffer storages included, the efficiency basically improves. Okay, the performance of the automated production line is going to be better. So we'll just break for 10, 15. Okay, we'll just break for 7 minutes, and we'll get back at 12:55 so that I can close the class at 1:30 sharp. After this, we'll just discuss those equations and solve one solved problem from the textbook, and then we'll finish off with this unit 2. So we'll just meet after 7 minutes. Yes.
Yes, ma'am.